Okay, so we know what a definite integral is. And so what if we wanted to actually evaluate one? Because it's an area under often a curvy thing, which we don't really know how to find curvy areas, sort of. We haven't been able to before calculus. And so let's just look at an example briefly. Let's look at, a pretty easy function, but not a straight line, the y equals x squared function. So it comes in like this, and then it goes like that, right? So f of x equals x squared, or y equals x squared, doesn't really matter how you say it. And say I just want the area from 2 to 5. So let's just say from like x equals 2 to x equals 5, I want the area. And so it's this, oh my God. It's this area right here, right? That we're trying to find. And so this is this right here, we just said we write it as the area. Everything's above the x-axis, so it's a positive area. So we don't have to worry about it being a signed area. It's the integral from 2 to 5 of x squared dx. Okay, and if we, that's the way we write it. And if we think about how we could do this, we could sort of start thinking, well, we could do a Riemann sum, right? We could start drawing rectangles, make them fit. We get some sort of approximation of the area. We could do it with like 4 rectangles by hand pretty easily. We could make a computer do like 100 rectangles or 1,000 rectangles. We'd actually make a computer do like 1,000,000 rectangles and pretty much guess what the area is going to be. It'll be something, but it'll be like plus a little bit, And if it turns out the area is a weird number, then you might not recognize exactly what the number is. So, so let me just say, like, if we really wanted to get an exact area, right? So remember what this is. It's actually the limit of the Riemann sums. And I could actually write it down. You can sort of check this yourself as a sort of, as a limit of Riemann sums. The area, the integral from 2 to 5 of x squared dx is actually, it's the limit as n goes to infinity. So if you wanted to do I'm just going to say like a right Riemann sum with n rectangles, and I'll actually write it down for you, right? So well, maybe I'll write it first, just to remember. It's like f of xi delta x. But if I think about delta x is actually, you're taking an interval of width 3, divided it into n equal pieces. So there's going to be a 3 over n here for delta x. And then we're going to have something squared. That something's going to start at 2. And then you can remember that what it really is it's, maybe I'll write it in red down here. It's really f of 2 plus I delta x. You're just counting the number of delta x's you're going over times delta x. And so you get basically 3i over n right here. And this looks kind of horrible, right? I mean, you could imagine evaluating this for specific, for n equals 4, or for n equals 100, whatever. Let me just make a note that this is a right Riemann sum. Actually, the only difference for left is I would just go from 0 to n minus 1, right? Right, correct. I mean, correct. I would go from 0 to n minus 1 for a left Riemann sum. So this is this limit. And it turns out, like, if you were going to try to actually evaluate this limit, first off, you'd have to evaluate the sum. So yeah, if we wanted to evaluate this, first evaluate the sum. And by that, I mean, rewrite the sum just as a function of n, i.e. rewrite, because we need to be able to take the limit as n goes to infinity. And this sum is kind of like an ugly thing. Like, I don't know how to take the limit as n goes to infinity of this because you're adding in things together. So even having the n's on the bottom, maybe you think these would go to 0 or something, but you're adding more and more together. That's the whole point, is it's not actually going to 0, it's actually turning into the area under the curve. So this is kind of a hard problem, right? So rewrite as a function of n. But then the question is, how? And I will say it's not impossible for this example because this is a pretty simple curve. You can actually do it. I've sometimes taken Brave classes through this whole argument, and they've never really liked me for it. But it is possible to actually go through all of this. I claim it's possible to actually sort of find the sum. I guess you could ask me in office hours or something one day if you really wanted to go through it. You can actually find the value of the sum and then take the limit as n goes to infinity and actually get the right answer. It's kind of astonishing. But that's only because this function is so simple. It's a squaring function. If I did the same thing with like the sine function, sine, the trigonometric sine function, or like log or something, I have no idea how to get a nice closed formula for those sums. And so it just really becomes, this is a difficult problem. This is really hard, is my point. And it's okay. It's just really not fun, not something you want to do. This is really hard in general. So it really, even having the Riemann sum idea, doesn't feel like we're that close to actually finding areas under curves. But that's where the fundamental theorem comes through and does this magic thing, right? So, so I'll just say the fundamental theorem comes to the rescue. And that's why we have to respect the power of it. Because any sort of like follow your nose method of trying to find this area is just going to give you approximations, and it's not going to be clear at all how to generalize or how to get the exact answer. So that deserves an exclamation point, I think. So let me just give the statement of it, right? The statement, which it seems just that a lot of you have seen before, is that if we want to evaluate, so given a function f of x, turns out, you could give criteria on the function, like, let's just say define. I mean, you sort of should say it's at least continuous or continuous except at certain point, or finite number of points or something like that. Some sort of weird conditions, but I'll just sort of gloss over that. So given a function f of x defined for a less than equal to x less than equal to b, and let so the book uses capital F, but I'm just gonna use a different letter just so I don't mix up my lowercase f's and capital X. So let g of x be an antiderivative. So I'll use capital G. An antiderivative of little f. In other words, it's just saying that capital G prime is little f, right? The derivative of capital G is little g. Then this amazing thing happens. The integral from a to b of f of x dx, all you got to do is find this antiderivative, plug in the endpoints, and subtract. It's g of b minus g of a. So, in words, it's plug endpoints into the antiderivative and subtract. Okay. And this is amazing. It's gives us a way to very easily evaluate, find the areas under lots of weird curvy things. And let's just go back to the example. So in our example, just to illustrate this, f of x is x squared, a good choice for g of x, if you just think about a function whose derivative is x squared, is 1/3 x cubed. Right, you could use, I mean, it turns out there's more than one antiderivative. 1/3 x cubed plus 5 also works because the plus 5 goes away when you differentiate it. But this is a nice choice because there's no reason to add a constant. Then the integral from 2 to 5 of x squared dx is g of 5 minus g of 2. Another way we write this is we'll just write 1/3 x cubed. And we do something that almost looks like this integral sign right here, but we use vertical bar and we write the 2 and the 5 at the top and bottom. That's just a notation that means like plug in the endpoints and subtract, plug in. Yeah, this is a notation. For plug in endpoints and subtract. You just kind of want to do this to keep track of the endpoints, and you don't want to have to, it's nice not to have to actually refer to the function by a letter name, you know. To have to explicitly say like this is f and this is g. So that's 1/3 x cubed from 2 to 5. And so if we actually plug that in, we get 1/3 times 5 cubed minus 1/3 times 2 cubed. 5 cubed is 125, 2 cubed is 8, all over 3. Turns out that's 117 over 3, and 117 happens to be a multiple of 3. I chose it that way, and when you divide by 3, I think you get 39. So that is the area. That's the area. This is the area all the way back up. Where'd I go? It's up here somewhere. That is that area right there. It's actually area 39. It might look a little bit like you can sort of ballpark yourself to see if the numbers make any sense. Like that's height 4, that's height 25. So there is this rectangle here that's like 25 by 3, which is 75. So 39 is a plausible answer, right? I mean, it's more than half the area of that rectangle. Half of 75 is actually 37.5. So it's just a little more than half the area of the rectangle. So plausible, and that is the answer. And it's amazing, again, that the real point is that the fundamental theorem of calculus is amazing. You did not want to do this sum. I could show you this sum gives you 39. For any harder function I couldn't show you, it gives the right answer. But it's still tedious and ugly, and this was almost instantaneous. So just, my big point of this video is respect the power of the fundamental theorem of calculus. All right, I'll stop.